everyone. My name is Yizheng. I'm going to present our paper, Cost-Aware Robust Tree Ensembles for Security Applications. This is joint work with Shiqi, Weifan, Asaf, and Suman from Columbia University. We use tree ensembles such as random forest and gradient-boosted decision trees for many different security applications. For example, we train tree ensembles to detect malicious autonomous systems, malware, social engineering, and phishing emails. Since tree models are very popular in security, we want to increase their robustness against evasion attacks. However, the robustness of trees has not been thoroughly studied compared to other models such as neural networks. And existing works on the robustness of trees do not apply to security applications very well. Previous works have formulated the evasion attack against tree ensembles as the following. The attacker's goal is to make small changes to a malicious sample, such that the tree ensemble misclassifies the sample as benign. In particular, researchers have modeled the small changes using the LP norm threat model. They asked the following question for robustness verification of a tree ensemble model. Does there exist a perturbed malicious sample within a bounded LP norm distance such that it is classified as benign? If the answer is no, then the malicious sample is verified to be robust under the threat model. However, LP norm distance is not suitable to model the realistic attacker's capabilities to evade security classifiers. We use a simple example of the Young infinity norm threat model to demonstrate the reason. Here, we have two data points, one malicious and one benign, and we plot them along feature x1. The Young infinity norm threat model bounds the attacker's perturbations symmetrically in the dotted lines. Along feature x1, the split x1 less than eta can separate the data points and their corresponding L infinity norm bounded region. On each side of the split, the classifier can correctly output the malicious and the benign prediction. This is a robust split, since the attacker cannot evade the classifier by perturbing either data point within the bounded L infinity norm. However, in practice, feature manipulation cost is asymmetric, which cannot be captured by the L infinity norm threat model. We show an example that for the malicious data point, it is easier to increase feature x1 than to decrease it, and it is hard to perturb the benign data point. This is often the case for malware authors to evade the malware classifier. It is easy to insert redundant content in the malware, but it is hard to remove content from the malware, which may compromise malicious functionalities. In addition, it is usually hard to change benign data samples outside the attacker's control. Under the realistic threat model, the split x1 less than eta is no longer robust. If the attacker moves the malicious sample to the shaded region, then the sample will be misclassified as benign, which is a successful evasion case. Therefore, we propose a new cost-aware threat model to capture different feature manipulation costs for the attacker. Then we can find out that the new split x1 less than eta prime is more robust than the previous one, since the samples cannot be perturbed to cross the new split. To represent our cost-aware threat model, we propose the cost constraint function that maps each feature value to an interval of allowed changes. Using security domain knowledge, we can specify the cost constraint function for different features of different security classifiers. Since our goal is to train robust tree ensembles, this raises the question, given the cost constraint function, how to find the robust splits? We designed our robust training algorithm by reevaluating the quality of the split given an arbitrary attacker bounded by the cost constraint. In the regular training algorithm, We evaluate the quality of the split without considering how an attacker may perturb the training data points. At a high level, we first sort the data points along a feature dimension x1. Then we compare all the possible splits between every two consecutive data points. Here we have two candidate splits, x1 less than eta 1 and x1 less than eta 2. We want to know which split is better. While there are different scores to calculate the quality of the split, here we use information gain as the example. Comparing the information gain of the two splits, we can see that the first split, x1 less than eta 1, has a higher information gain, and thus it is better than the second split. Now, what if the attacker can perturb the samples to cross the split? How can we compute the quality of the split? For simplicity, we assume the cost constraint that the attacker can increase every data point by up to the same amount alpha and decrease it by up to beta. The first thing we do is we translate that to the attacker range, which reverses the interval around the data point to one surrounding the split. Here, the attack range is between eta 1 minus alpha and eta 1 plus beta. All data points within the attack range can potentially be moved across the split, but all data points outside the range cannot. Then we compute the worst information gain as if the attacker can maximally degrade the quality of the split. Since we have two data points that can be moved, each data point has two choices to be either on the left side or the right side of the split. There are 4 cases in total. By enumeration, we know that moving only the cross data point to the right side has 0 information gain, which is the worst information gain in all cases. Then we do the same to compute the worst information gain for the second split. Since no data points can be moved across the split in this case, the worst information gain is the same as the original one, which is 0.251. Comparing the worst information gain for the two splits, the second split has a higher score, and therefore it is a preferred split. In general, when there are n data points within the attack range, the attacker has 2 to the n different ways to reduce the split quality. Enumeration is intractable, since this needs to be repeatedly computed for all splits during the training process. So the question is, how to efficiently compute the worst score for each split? To solve this problem, we propose a greedy algorithm to compute the approximate worst quality of each split. Our algorithm works for different metrics used to evaluate the split quality, including information gain, Guinea impurity, and cross-entropy loss. Then we pick the split which has the best worst-case quality to be the robust split. We have implemented our robust training algorithm for both scikit-learn and XGBoost, and we have applied it to Twitter spam URL detection as a case study. The task is, given a tweet containing a URL, we want to train a robust tree ensemble to detect whether it is a spam URL. A spam URL posted on Twitter is the initial URL. It will go through a series of redirections, and then the URL redirection chain will reach a malicious landing page. We re-extracted 25 features proposed in related work from URL redirection chains and graphs to detect Twitter spam URL. Then we specify 4 categories of cost to increase or decrease each feature. The categories are negligible, low, medium, and high cost. As an example, for the feature number of domains for landing page IP addresses, we specify the following cost constraint. We specify that it is low cost for attackers to increase the feature, since the attacker can simply reuse the same landing IP address to display more malicious landing pages. However, we specify high cost to decrease this feature because the attacker needs to purchase new hosting services to host additional malicious web pages, which could have been hosted on the same IP. The allowable changes by the attacker for each cost category is the parameter. And we have experimented with four cost families and 19 cost models in total to compare the trade-off between robustness and accuracy for different cost models in our paper. Our key result from our evaluation is, using our new training algorithm, we can increase the adaptive attack cost by 10.6 times. For our cost this is the increase for our cost-aware robust model compared to a baseline XGBoost model. In order to gain robustness, our robust model has modest decrease in accuracy and increase in false positive rate. For interested readers, our paper has more evaluation results, including comparing our training algorithm with different baseline algorithms across different benchmark datasets and analysis of training different cost models. Our robust training algorithm works with both scikit-learn and XGBoost, and we have released our source code and models in the following link. Thank you for listening to the talk, and I'll be happy to answer any questions during the Q&A session.